Hello again to our next video about functional mockup in interface in industry. Part 7 is about FMI in industry and about the tools we at EKS are using. So this time it will be more practical. Let's get into it. FMI is already used in industry. Some examples are Festo, which are describing their switching behavior of their pneumatic cylinders using FMUs, SEV using frequency converters, or providing models for their frequency converters. ABB Robotics provide complete virtual robot controllers as FMUs, and even the big industry 4.0 formats, automation ML and asset administration shall suggest FMU for exchange of simulation models. And in virtual commissioning, where EKS is mainly focused, the model world is not yet very useful, or not yet very present. The most popular virtual commissioning tools like Siemens Simit, the EKS RF Suite, WinMod, etc. are getting traction in FMU and start to support FMU, but it's not widely spread. Classically, the simulation models are exchanged on tier level. So you have the different depth of vendors that are together building a production chain, and typically you get your models from your vendor you buy your components from, and before you integrate them you do some actual prototype testing to test if this would work. In fact, this reduces the work for the model providers because they don't have to provide arbitrary, complex and detailed model, and you have the option to do some inter-domain model exchange, like you have some electronical models and you use them, for example, in automation systems, and then you can reuse what you have already modeled in electronics there. Nevertheless, FMI is rather small, so this exchange of models is not so common, and hopefully it will get more traction soon. But we see already that the relevance increases, and once the big players request FMU from their vendors, then it gets really big business, because then money is behind it, then there is money behind it, and then it's no longer scientific or theoretical, but then it's practical, it's hard money, and then people start thinking really about it. And you have to say that at the moment FMI2 is state of the art, meaning that if an OEM asks for an FMU, then it will be FMI2. FMI3 is under evaluation, but there is no breaking change or no breaking feature out there that the OEMs at the moment say, okay, we need FMI3. This can change depending on the use cases of the big players. At EKS, we are doing virtual commissioning as one part of our daily job. So we are in the context of a production plant of a big player, and we have some software and some programs from different sources all over the automation system process, and we want to incorporate all this software and include some physical hardware, or some virtualized physical hardware is also possible, and to check if it works together or it will just break the complete system. And there are different aspects that we are possibly looking at. There is, for one, the compatibility, so are the different software assets compatible to each other? Then there could be some special edge cases that we could try out, like the ramp up of a production plant, going into maintenance or even emergency stops, without actually stopping a complete production plant and the production line even. And then there is the collision detection, which is also a specialty of EKS, where we want to check if there is a chance that due to errors in some programs of, for example, robots, some undetected errors in the future, at some point there might affect a collision. You can think of this way. The robot programs are taught in and are typically running in a continuous production line. So it's serious production, there is no stopping, there's everything in sync, nothing serious happens. You don't see any problems there, it's working. At some point one robot has a problem. For example, it needs some maintenance. Doesn't matter what it is, just a small thing that gets the system out of sync. Or someone opens a door, could also be the case. So the complete system gets out of sync, and ideally the robots would have a collision avoidance and collision, there are so-called collision zones. That means if one robot is in a collision zone, no other robot may enter it. And if this was forgotten for one robot, then another robot could enter the zone and hitting either the other or getting hit by the other robot, and this causes really some costly impact. So we want to avoid that if at all possible. So we have to think a bit how EKS thinks about virtual commissioning, then you might get a bit more idea of it. So we start at the planning phase, more or less. Planning, floor planning, how this complete production plant is going to be built. Then there is the engineering, where we decide how the robots could handle the tools involved. And in the end we have the simulation. So at this point we have the idea how this production plant could look like, how this production plant could work. From there we get into virtual commissioning. Virtual commissioning means we plug in all pieces, we put in the software, we hit the virtual play button, and we check if things are working. If this is true, we go into commissioning. So we do this in real world. We do not do this only for theoretical purposes in the computer, but we actually do this in real world. And in the real world then we have first this interlock check, which is what I just described with this checking about collisions. We start to ramp up, that means to actually start producing with the plant. We run the plant, we maybe use the plant to train our operators, our workers in the field. So at this point the company starts producing. And then we have the last section that closes the process, which is the optimization. So at some point we see, okay, we have a suboptimal process defined here. For whatever reason, either the product has changed or we see that there is optimization potential, or for whatever reason. And then we start the same process again. We plan again. We start from the brownfield plant. We start from what we have. We redo what we had done. If it's necessary, we can reuse things, or we can redo from scratch, depending on what's necessary. We start again with virtual commissioning to check if the changes would actually cause problems. And then we are doing also this modification in a ramp up, and we start again and optimize the process again. So this is about this, we call it laying 8 because this is a procedure we are oftenly referencing as the main idea behind our products. And I want to show you some products. One is RF Scout. This is this interlock check things. We have these safety zones for robots, and they must be used correctly. And in fact, theoretically, it's not that easy, because you have to check all combinations and all permutations, and they are not testable because you don't. You cannot in a real world just put the robot in any location and just say, okay, do it, because you would have to program it there. And as I already mentioned, there could be some issues during maintenance, up down, emergency things, ramp up, ramp down, where the robot gets in a situation which is not serious production, and then sometimes issues arise that you are not aware of and you don't want to have them. So the idea of RF Scout, you collect a rather large data set. Ideally, you have some of these special cases included. And then there is a static analysis where you check if certain conditions are met, like if there are, for example, if there are any safety zones defined that are never used for a robot but should be used, there could be a problem. Or if two robots interact with each other, then each of them must use the same safety zones. If there are no common safety zones, they cannot interact. So something like this. These are some rules that are defined. I think there are a few dozen rules there in this Scout stuff. And in fact, what it is possible is to detect these collisions before they happen. So this is really nice feature to just go to the robot program and say, hey guy, you did something wrong here, please check that code again. Then we have RF Guard. RF Guard is the process of mechanical design automated, not with AI, but with rules. We have typically many fixtures that we need to design, and they are very common and very similar, but are nevertheless customized. So we would like to use off-the-shelf components, but it's not always possible, and we always have to keep in mind that our customer has some restrictions regarding what must be reachable. Typically there are welding processes involved, and this welding gun can only to a certain amount of length get where it needs to get, and we need to make sure that it's possible to reach all required welding points. And classically you do this manually, but this is tedious and does not make much fun. So there is the idea to make these constructions automatic or semi-automatic. You put there your CAD file that you want to work on, you define at which positions the grippers might grab this part, and you define the welding positions, and in the end you hopefully get some good construction. Typically you have to do some manual post-working or some manual selection because you get multiple solutions, but nevertheless this saves significant amount of time if the problem is not too complex. For too complex systems, the time taken by RF Guard is so high that you will not be able to wait until it's finished and to see if this result is feasible or not, but instead you will most probably have to work on your own. And now FMI comes into play, because we have at the moment virtual commissioning simulations that are very optimized. That means we have a real-time simulation of a production line which can be run on a normal consumer hardware, more or less. Consumer, yeah, okay, it's business consumer, but it's consumer, so a normal laptop is sufficient to run a complete production plan. This is only possible because our software is so tailored down for this use case, And what we especially have dropped is physical. All physical simulation is out, and there is no option to do this, to do physics. We could add some components, but these components need manual modeling, and this is always heuristical, so this is not very useful. In the sense that if you really need physics, you have some sort of a problem. And here FMI comes into play, because the idea is to use FMI for just this narrow use case to add the physical layer to our virtual commissioning solution. And we can then only piecewise zoom in at certain points where we say, okay, this should be physical and this should be physical, and the rest can be only signal based, and it's fine. Because then it's still rather fast, and we don't have the problem that everything needs to be simulated in physical engine, while still being able to have certain aspects of the physics involved. And finally, I want to give you an excursus about security and simulation. And in FMI, I already mentioned, you can put models as black box out, and this is done by just providing only the DLL. And the problem here is that theoretically there is an attack vector possible, and to execute arbitrary binary code on your vendors or whatever who you give your components to machine. So in industry, this is a no-go. You may not execute such an FMU. And here I'm personally involved because it's my PhD that I'm at the moment doing. There's still some work to do. I plan to create a layered standard for that. And if you have any discussions or questions, you can write it down. I try to answer, but I cannot guarantee. Okay. Okay, this was about FMI in industry, just a rough overview of what's possible and what's done so far. This is the last video so far in this series. There will most probably be a video about security, but this will be held separately, and if you have more questions or more ideas, you might have already sent a message to us or send a message to a comment, and we will look into them. Eventually we can add one or more videos to it. Thanks for watching, and hopefully we see each other again. Bye.